Sanjay Kumar. He completed his BE Civil Engineering from Madurai Kamaraj University. He also pursued his ME Soil Mechanics and Foundation Engineering from Anna University, Chennai. He worked as a designer engineer for 1 year under a structural consultant in Madurai. He is currently working as a faculty member in the Department of Civil Engineering, Tyagarajar College of Engineering, Madurai. He has organized 2 national conferences at TCE in 2010 and 2014. He's also got 3 publications in international journals. He is an A-lead member for the Geotechnical Consultancy at Tyagarajar College of Engineering.
Welcome to UGC lecture series for architecture. Name of the subject is Mechanics of Structures 1 and we are in unit 5, elastic constants. This will be lecture number 13. Contents of this lecture are as follows. First of all, we will be seeing an example problem for calculating the bulk modulus of a bar subjected to stresses along 3 mutually perpendicular directions. Then we will be seeing the definition for shear stress, shear strain and shear modulus, also called as rigidity modulus. Next, we will be obtaining a relationship between Young's modulus and shear modulus. Finally, we will be deriving a relationship between the 3 elastic constants, namely Young's modulus, rigidity modulus and bulk modulus. We shall see a problem. A steel bar 25 centimeter long and 5 centimeter by 5 centimeter in cross section is subjected to a tensile load of 300 kilonewton along longitudinal axis and compressive loads of 500 kilonewton on each sides. Under the action of the above loads, the change in volume is observed to be 0.05 centimeter cube. Determine the value of Poisson's ratio and bulk modulus. Take Young's modulus capital E equals 2 into 10 power 5 Newton per millimeter square. Now, we have a bar. The cross section of the bar is a square, length of the bar is 25 centimeter, breadth is 5 centimeter and the thickness is also 5 centimeter. Now, we shall consider the 3 axes. So, this will be x axis and this will be y axis and this is z axis. Along the longitudinal axis, we have a tensile load of 300 kilonewton. So, tensile load 300 kilonewton, it is acting along the longitudinal axis, which will be the x axis. On the 2 other sides of this square bar, we have compressive force of 500 kilonewton. So, along z direction, a compressive force of 500 kilonewton is acting. Similarly, along y axis, a compressive force of 500 kilonewton is acting. Change in volume of the bar delta V is given 0.05 centimeter cube. You are asked to determine the value of Poisson's ratio, which is 1 by m, and the bulk modulus. Bulk modulus is K. So, these two are the quantities which are to be found out. Now, we shall calculate the stress along x axis. Stress along x axis, force along x axis is 300 kilonewton, it is tensile force. So, we shall convert the force into Newton. So, 300 into 10 power 3 divided by cross section area perpendicular to this 300 kilonewton tensile force. Cross section area perpendicular to this 300 kilonewton force is 5 cross 5, 5 centimeter cross 5 centimeter. We shall substitute the value of cross section area in terms of centimeter square. So, 50 cross 50, which will give us 120 Newton per millimeter square. The nature of stress is tensile. Now, we shall calculate the stress along y axis. So, this is the direction of y axis. Along y axis, we have compressive force of 500 kilonewton. So, stress along y axis will be force by area. Force is 500 into 10 power 3 divided by area. Area perpendicular to this 500 kilonewton force is length of the bar 25 centimeter cross the thickness. So, length cross this thickness 25 centimeter is 250 mm cross the thickness is 50 mm. So, the value will be 40 Newton per millimeter square, but this is compressive stress. Likewise, we shall calculate the value of stress along z axis will be. So, this is z axis, load acting along z axis is once again 500 kilonewton compressive force. So, which will be 500 into 10 power 3 divided by area normal to that force is this 25 centimeter cross 5 centimeter. So, 250 into 50, which will give us same 40 Newton per mm square compressive. So, stress acting along x axis is denoted as small p suffix s, stress along y axis is denoted as small p suffix y, and stress acting along z axis is small p suffix z. After calculating the stresses along the three directions, we shall calculate the value of strain along the respective axis. Strain along x axis is given by epsilon x, which is given by stress along x axis P x divided by Young's modulus of elasticity E. Now, we shall once again go to the previous slide. If you see the nature of stress acting along the three axes, P x is tensile. Let us once again recollect that all tensile stresses will have positive sign. So, tensile stress will have positive sign and compressive stresses will have negative sign. So, stress along y axis and stress along z axis are compressive in nature, and hence P y and P z alone will have negative sign. P x is a tensile stress and hence it will have a positive sign. Now, for this equation, that is for the strain along x axis, P x divided by E, P x is positive because of tensile stress, minus P y is compressive in nature. So, we will be having minus P y divided by M E minus of P z. P z is once again compressive in nature. So, we will be having another minus sign here, minus P z divided by M E. Now, we shall substitute the value of P x, P y, P z and E here. P x is 120 Newton per millimeter square divided by E. At this stage, we will not be substituting the value of E, plus minus of minus you will have plus. So, plus P y. P y is 40 Newton per mm square divided by M E plus P z is also 40 Newton per mm square divided by M B. So, if we add all the three, you will get 120 by E plus 80 divided by M E. So, this is the value of E x. Likewise, strain along y axis will be given by E y, which will be P y by E, where P y is the direct stress acting along the y axis, but that stress is compressive in nature and hence we have to put a minus sign here. Then minus of the strain acting along the other two axes, which will be strain acting along x axis and strain acting along z axis. Strain acting along x axis will be P x divided by M E. Now, since P x is a tensile stress, we have a positive sign here. Then minus P z divided by M E. P z is a compressive stress, so we will have a negative sign P z minus P z divided by M E. So, we shall once again substitute the values. P y is 40. So, minus 40 divided by E minus P x is 120 divided by M E, minus of minus will be plus P z is once again 40 divided by M E. So, we will be having minus 40 by E, then minus 120 plus 40, will be having minus AT by ME. Finally, we shall get the value of strain along Z axis epsilon Z will be PZ by E. Since PZ is compressive stress, we should put a minus sign here, minus Px by Me. Px is tensile, so we have a positive sign here. Minus Py by Me. Py is compressive in nature, so we will be having negative sign Py by Me. So, we will be having Pz is 40 Newton per mm square. So, 40 by E minus 120 by Me plus 40 by Me, which will be equal to minus 40 by E minus 80 by Me. So, epsilon y and epsilon z, strain acting along y and x axis are same. Now, the volumetric strain is epsilon v, which is given by delta v by v, is sum of the strains induced along x, y and z axis, epsilon x plus epsilon y plus epsilon z. Epsilon x is 120 by E plus 80 by Me minus 40 by E minus 80 by Me. Again epsilon z is minus 40 by E minus 80 by Me. So, this plus 80 by Me minus 80 by Me will cancel out with one another. This is 120 by E, these two will be minus 80 by E. So, we will have 40 by E minus 80 divided by Me. So, this will be 40 by E can be taken out, 40 by E into 1 minus we will have 2 by M. So, this is the volumetric strain delta V by V. From this we shall get the value of 1 minus 2 by M alone. So, 1 minus 2 by M will be delta V by V into E divided by 40. So, 1 minus 2 by M will be delta V by V into E divided by 40. Delta V is given as 0.05, that is change in volume. Change in volume is observed to be 0.05 centimeter cube. So, 0.05 volume should be substituted in centimeter cube. So, length is 25 centimeter into breadth 5 centimeter into thickness 5 centimeter. So, this is delta V by V into strain, which is 2 into 10 power 5 Newton per millimeter square divided by 40. From this 1 minus 2 by M will be equal to 0.4. From this we can get the value of 1 by M. 1 by M will be equal to 0.3. So, this is the value of Poisson's ratio. Next, we are also asked to calculate the value of bulk modulus of elasticity. So, we shall use the relationship between Young's modulus and bulk modulus. E is equal to 3k into 1 minus 2 by M. So, we know the value of E is 2 into 10 power 5, which is in Newton per millimeter square, which is equal to 3k. K is the bulk modulus, which we need to find out now. 3k into 1 minus 2 by M. 1 by M is 0.3. So, 2 by M will be equal to 0.6. Simplifying this, the bulk modulus K will be coming as 1.66 into 10 power 5 Newton per millimeter square. Now, we shall see the definition for shear stress. A section will be subjected to shear stress if the force is acting tangentially across it. Now, let us consider a cube which is fixed at its base. So, A, B, C, D is the cube with the side A, B rigidly fixed at its base. Over the top surface, let us consider a force acting tangentially over it. that is at the top surface we have a force of magnitude P acting along it or acting tangentially over it. Because of this tangential force, the side DC will be displaced to D dash and C dash like this, whereas the side AB will not suffer any displacement because it is fixed at its bottom. So, this cube will deform in this manner. The angular deformation is denoted as phi. So, let L be the side of the cube, side dimension of the cube. So, over the top surface DC we have a tangential force of magnitude P. So, the top surface is going to experience shear stress. The intensity of shear stress as per the definition will be the tangential force, the magnitude of tangential force divided by the area of the face DC. Area of the face DC or the top surface will be a square one. So, it will be equal to P by L square. So, the shear stress will be equal to tangential force divided by area resisting that tangential force. So, P is tangential force, or we can also call it as shear force. Now, shear strain will be measured in terms of the angular deformation. So, shear strain is phi. So, this is the angular deformation which the top side DC is going to experience. So, phi will be, now this angular deformation is a very small angle. So, if you take tan of phi, now this is a right angle triangle, triangle A D dash D is a right angle triangle, in which if you take tan phi we will get D D dash divided by AD. Now, this phi being very small, tan phi will be approximated to phi. So, phi will be equal to D D dash by AD, which will be equal to C C dash divided by BC. So, this angular deformation is known as shear strain. Now, we shall see the definition for shear modulus or modulus of rigidity. Modulus of rigidity is denoted by the alphabet capital N. Shear modulus is the ratio of shear stress Q to the shear strain phi. So, it will have units just that of stress. So, its unit will be Newton per millimeter square or kg per centimeter square or tons per meter square. Now, we shall see the relationship between Young's modulus and rigidity modulus. Let us consider a cube AB CD. The top surface is subjected to a shear stress of intensity Q. So, Q is the intensity of shear stress acting over the top surface. Because of the shear stress, the side DC will be displaced like this. The corner D will be displaced to D dash and the other corner C will be displaced to C dash. So, this angle is phi, which is shear strain. Now, let us join B D dash and B D by a full line. Now, the corner D is displaced to D dash and the corner C is displaced to C dash. The original diagonal is B D. Now, this diagonal will be elongated to B D dash. Let us draw an arc of radius equal to the length of the diagonal B D from D. So, this is that arc. So, radius of this arc is the length B D. This arc is drawn with the center point as B. So, let us name this particular point as D double dash, D double dash. Now, let us consider this small triangle D dash, D and D double dash. So, I am drawing it here. So, this point will be D dash, this point is D double dash and here we have D. the angle D D dash D double dash will be more or less 45 degree. Actually, it will be slightly less than 45 degree only by a very small amount, hence this angle can be taken as 45 degree. So, this angle D dash D double dash D will be more or less 90 degree. So, this triangle will be a right angle triangle. Now, if we take cos of this 45 degree angle, cos of 45 degree, we will get the adjacent side D dash D double dash divided by the hypotenuse D D dash. So, D double dash will be equal to cos 45 into D D dash. The diagonal BD will elongate and the other diagonal AC will contract. Because of the direction of the applied shear stress, BD will elongate into BD dash, whereas the diagonal AC will be shortening into AC dash. Now, we shall calculate the strain induced on the diagonal BD. Strain on the diagonal BD will be tensile in nature. Strain is change in length. Change in length of the diagonal BD will be D dash D double dash divided by original length of the diagonal. Original length of the diagonal will be BD. Already we have obtained the value of D double dash as cos 45 into D D dash divided by BD. Now, let us consider this triangle. This is A, B and D. Now, this is the diagonal of the cube. So, this angle will be 45 degree. Sin of 45 degree will be equal to AD divided by the hypotenuse BD. BD will be equal to AD by sin of 45 degree, AD by sin of 45 degree. So, we shall substitute the value of BD as AD by sin of 45 degree. So, the strain will be equal to D D dash into cos of 45 degree divided by AD divided by sin of 45 degree. So, we will have, so if we bring the sin 45 in the denominator to the numerator, we will have cos 45 degree into sin 45 degree, which will be 1 by 2. So, 1 by 2 into D D dash divided by AD, but we know that D D dash by AD is shear strain. So, this will be equal to 5 by 2. So, therefore, strain on the diagonal BD comes as 5 by 2, shear strain by 2. Now, we shall calculate the tensile strain induced on BD due to the tensile stress induced along BD. So, strain on BD due to tensile stress, because BD is elongating. So, it will be experiencing tensile stress. So, strain on BD due to the tensile stress on BD will be given by, we know that strain is the ratio of stress to Young's modulus. Here the stress is shear stress, which will be Q divided by Young's modulus of elasticity E. Strain on BD due to compressive stress on AC. If you see this picture, the diagonal AC is getting compressed to AC dash. So, because of the compressive stress on AC, there will be some amount of strain along BD. That strain will be given by minus 1 by m into Q by E, because this is lateral strain. Strain on BD due to compressive stress on AC will be lateral strain. So, Poisson's ratio times stress by Young's modulus. Since it is compressive in nature, this stress is compressive in nature, we will have a minus sign here. Therefore, total strain on BD will be Q by E minus of this particular strain, the second one, strain on BD due to compressive stress on AC, which will be minus 1 by m into Q by E. So, we will be having Q by E plus Q by ME. We can take Q by E outside. So, we will be having 1 plus 1 by m, Q by E into 1 plus 1 by m. So, Q by E into 1 plus 1 by m is the strain on BD which is calculated. Already we have calculated the strain on BD as phi by 2, that is phi by 2 here. Now, phi is shear strain, shear modulus or rigidity modulus is the ratio of shear stress to shear strain phi. So, from this equation phi will be equal to Q by N. So, substituting the value of phi here we will be getting Q by 2 N. So, this Q and this Q will cancel out. From this we can get E will be equal to 2 N into 1 plus 1 by m. So, this is the relationship between the rigidity modulus N and the Young's modulus of elasticity E. Now, we shall see the relationship between the three constants of elasticity E, K and N. Now, we have derived E as 2 N into 1 plus 1 by m, or 1 by m will be equal to E by 2 N minus 1. We shall take this as equation number 1. Now, Young's modulus of elasticity in terms of bulk modulus will be E is equal to 3 K into 1 minus 2 by m. So, in the same manner, if we simplify this equation, 2 by m will be equal to 1 minus E divided by 3 K, or 1 by m will be equal to 1 by 2 minus E divided by 6 K. Let this be equation number 2. On the left hand side of these two equations we have 1 by m, therefore, E by 2 N minus 1 will be equal to half minus E by 6 K. So, if we simplify and rearrange this equation, we will be getting E as 9 K N divided by N plus 3 K. This is the relationship between the three elastic constants, namely Young's modulus E, shear modulus K and rigidity modulus N. E is equal to 9 K N divided by N plus 3 K. To summarize the things which we have learned in this lecture, we have seen the definition for shear stress, shear strain and shear modulus. Then we obtained a relationship between shear modulus and Young's modulus. Finally, we have seen the expression relating the three elastic constants. Following questions can be answered by the students. Obtain a relationship between rigidity modulus and Young's modulus. Obtain the relationship between the three elastic constants. Final question is a problem. In an experiment, an alloy bar 1 meter long and 20 mm by 20 mm in section was subjected to a tensile load of 6.4 kilonewton. If the length of the bar increases by 0.1 mm, calculate the value of Poisson's ratio. Take the bulk modulus K equal to 1.33 into 10 power 5 Newton per millimeter square. With this, we have come to the end of this lecture. Thank you.